Between Crossgates and Garforth, on the Leeds to Selby line, there is a bridge. It is carrying trains right now. The cast iron from which it was poured was smelted at Stanningley Ironworks and set into its arch between 1830 and 1834. James Walker, the engineer who designed it, also designed the parliamentary route it spans, despecifying a track bed of 66 feet, more than twice the width of any comparable line being built in Britain at the time, because he intended the railway to be built once and used for a very long time. He was correct. Crawshaw Woods Bridge is the oldest cast-iron railway bridge in the world, still in place over an operational railway. It has spanned the reign of 8 monarchs. It served as the primary access bridge to the Barnbow munitions factory during the First World War. The London and North Eastern Railway renewed its deck in 1943. Someone renewed it again in 1999. The cast iron arch ribs that hold all of this together are, in every structural sense that matters, original. They are also, and this is the part that tends to irritate people who have spent careers specifying modern steel replacements, still working correctly. The question is not why this bridge has survived. The question is what its designers understood about compression, mass, and the long-term behavior of brittle materials under load that the engineers who came after them gradually forgot. The reputation of Victorian cast iron as a bridge material is complicated by one well-documented disaster. In May 1847, at Chester, a cast iron girder bridge over the River Dee collapsed under a passenger train, killing 5 people. The Board of Trade Investigation, led by Captain James Simmons, concluded that the cast iron beams had been subjected to eccentric loading, a condition that introduced tensile stress into a material that tolerates compression well and tension very poorly. Robert Stevenson, who had supervised the construction, did not design a bad bridge. He used the wrong form for the material. This distinction matters enormously. Cast iron has a compressive strength the Victorian engineers measured in tons per square inch, and which modern assessments place in the range of 600 to 700 newtons per square millimetre. Its tensile strength is perhaps a quarter of that, sometimes less. In a beam, load is carried partly by compression in the upper fibre and partly by tension in the lower. In an arch, a load is resolved almost entirely into compression, through the span, down through the abutments, into the ground. James Walker knew this. He did not use beams. He used an arch. Specifically, he used a basket arch, a 3-centered arch where the height is less than half the span, with a clear span of 60 feet. The geometry was calculated to ensure that under the heaviest anticipated loading, the line of thrust would remain within the arch rib. The cast iron would never be asked to do the one thing it cannot do. This is not a structural accident. It is a structural decision made once in 1830 that is still being honoured by the physics every time a train passes over it. Before we continue, a brief interruption, which is more than this bridge has had in the last 40 years. If you find value in documenting the things that were built to last, the decisions, the specifications, the engineering principles that made longevity possible, consider subscribing. This channel exists because someone should be paying attention to these machines before the last person who knows how to maintain them retires and takes the knowledge with them. And if you have worked on something like this, maintained it, repaired it, sourced parts for a machine whose manufacturer no longer exists, tell us in the comments. What was it? How long had it been running? What did it take to keep it that way? We are genuinely interested. Unlike most comment sections, this one occasionally contains useful information. Now, back to the bridge. The casting process that produced the ribs at Crawshaw Woods was not, by 1830, a new technology. Abraham Darby had poured the iron bridge at Coalbrookdale in 1779, the first bridge of any kind built entirely of iron, its nearly semicircular arch of 30 metres exploiting precisely the same structural logic. Stanningley Ironworks, in 1830, was working with 50 years of accumulated knowledge about how grey iron behaves when it cools in a mould. Grey iron, specifically grey flake graphite cast iron, is not a single material in the modern metallurgical sense. The ratio of silicon to carbon, the pouring temperature, the cooling rate, and the geometry of the mould all influence the final grain structure. Victorian ironmasters worked by eye, by experience, and by the sound of the tapped casting. A good piece rang differently from a flawed one. This was knowledge that lived in the hands of the man who did the tapping, not in a written specification. What they produced, consistently, was iron with a very high compressive yield strength, poor tensile ductility, and excellent vibration damping. That last property is not incidental. A cast iron arch damps the energy of a passing train rather than resonating with it. The graphite flakes in the microstructure absorb and dissipate vibration at a rate that structural steel, which is far more homogeneous, far more elastic, cannot match. A steel bridge under repeated loading accumulates fatigue damage in direct proportion to the number and magnitude of stress cycles it experiences. A cast iron arch, keeping its load path in compression, imposes very low stress cycling on the material. So Crawshaw Woods Bridge was designed for horse-drawn wagons and early locomotives. The heaviest train it was originally expected to carry weighed perhaps 20 tons. Modern freight trains passing beneath it weigh in excess of 1,000 tons. The bridge has been assessed. It has not been condemned. This fact deserves a moment. Steel is the superior bridge material in almost every situation where the word superior is applied in modern structural engineering. It has a tensile strength of approximately 370 newtons per square millimeter in standard structural grades, matching its compressive strength with a consistency that cast iron never achieved. It is weldable, dimensionally predictable, and available in rolled sections to closed tolerances. It can carry a span of 300 meters without breaking a philosophical sweat. Or it has one disadvantage that its proponents prefer not to dwell upon. It is very good at carrying loads. It is, over time, progressively less good at carrying the same loads repeatedly. Steel fatigue is not a materials science curiosity. It is the governing design criterion for every railway bridge specification written to British Standards EN 1337 and the Network Rail Suite of Bridge Assessment Codes. S275 steel, the grade most commonly specified for railway structures precisely because stiffness rather than raw strength governs the design, experiences crack initiation at stress concentrations under cyclic loading. A welded joint is a stress concentration. A rivet hole is a stress concentration. A change in section thickness is a stress concentration. A modern steel railway bridge is a structure composed almost entirely of stress concentrations, experiencing millions of load cycles per year. A Network Rail's bridge assessment program routinely identifies steel structures requiring intervention at 40, 50, 60 years of service. The assessment process for a Victorian cast iron arch begins from a different assumption. The question is not whether the material has fatigued, but whether the geometry still keeps the load path in compression. In the majority of surviving Victorian cast iron arch bridges, the answer is yes. The Garforth Bridge on the same Leeds and Selby line, the only other iron bridge walker built on the route, was replaced in 2024. Not because the cast iron had failed, because it was easier to remove it and install a new structure with lifts on either side than to raise the original to accommodate electrification. The old bridge was donated to a heritage railway in Kent. It will presumably continue to carry loads there. Network Rail currently maintains approximately 30,000 bridges, tunnels and viaducts on the British railway network. Of these, many date to the Victorian period. Of those, a significant proportion are cast iron arch structures. The assessment methodology for these bridges evolved through the work of engineers, including Dr. Tom Swales, in whose research into 19th century cast iron beams, published in the Proceedings of the Institution of Civil Engineers in 1995, established the basis for understanding how Victorian ironmasters' production methods affected structural reliability. The fundamental conclusion was that arch geometry matters more than material specification when load path is in compression. The practical maintenance of a Victorian cast iron arch bridge is not complicated. The arch ribs themselves do not require lubrication, replacement, or scheduled overhaul in any conventional sense. The abutments require periodic inspection for movement. The deck requires renewal, as Crawshaw Woods has seen twice in its history. The parapets and balustrades require paint and occasional repair. The ironwork itself, if kept painted and the load path maintained, does not wear out in any meaningful engineering sense. This is what was meant, and what is often forgotten, by the Victorian phrase, designed for permanence, not designed to last a long time, and designed so that time is not the governing variable. In October 2025, engineers from the Transpennine Route upgrade carefully moved Crawshaw Woods Bridge using a 128-wheel self-propelled modular vehicle, an operation that took 2 days. The bridge was not dismantled. It was moved in a single piece. The abutments are being raised by 1.5 meters to accommodate overhead electrification. The cast iron arch ribs, the original wrought iron balustrade, the parapets, all are being repaired and refitted. The bridge will be reinstated in 2026 in precisely its original form, slightly higher. The engineers did not replace it. They adapted their infrastructure to retain it. That is the correct answer. The case of Crawshaw Woods is not unique. It is simply the most verifiable example of a pattern that repeats across Victorian cast iron arch bridges wherever the arch form was correctly applied. Consider the Victoria Bridge over the River Severn between Arley and Bewdley in Worcestershire. John Fowler designed it in 1859. It was cast by the Coal-Brookdale Company, the same ironmasters who had poured Abraham Darby's bridge 80 years earlier, and opened for traffic on the 31st of January, 1862. A single-span cast-iron arch of 200 feet, 4 arch ribs, each assembled from 9 H-section pieces bolted together. The ironwork alone weighs an estimated 500 tons. The Severn Valley Line closed to regular passenger services in September 1963. The bridge survived the threat of demolition. By 1974, the Severn Valley Railway had reintroduced heritage passenger services across it. It has been carrying steam-hauled trains in regular service ever since. The bridge deck was replaced. The ironwork was refurbished in 2004 at a cost of £320,000, the majority of which was spent on scaffolding, some because the bridge itself did not require that level of intervention. A 15-mile-per-hour speed limit is observed on crossing. This is not a structural limitation of the arch. It is a precautionary measure applied to all older structures regardless of condition. At the 2005 Historic Bridge and Infrastructure Awards, the Institution of Civil Engineers commended the refurbishment project. What they were commending, in essence, was the decision to keep what Fowler had designed, rather than replace it with something that would need replacing again in 50 years. The Coal-Brookdale Company is no longer casting iron arch ribs. The ribs they cast in 1861 are still carrying passenger trains. These two facts, placed side by side, say everything that needs to be said about designed longevity versus planned obsolescence. In spring 2026, Crawshaw Woods Bridge will be reinstated over the Leeds-Selby line. The cast iron arch ribs, cast at Stanningley Ironworks in 1830 and 1831, will settle back onto abutments that have been raised by 1.5 meters. New courses of stone dressed to match the original Bramley Fall gritstone beneath. Overhead line equipment will be installed above. Trains will run beneath. A new generation of electric services will pass under ironwork that was already old when the first electric railway in Britain was still a theoretical proposal. The bridge does not know this. It knows compression. It knows the geometry that James Walker calculated in a period when digital tools were not available, when calculations were made by hand, on paper, to a standard that has since proven correct for nearly 2 centuries of service. It knows the load path down through the arch, through the stone, into the ground. It has known nothing else since 1834. The question that this bridge, and the Victoria Bridge, and the Iron Bridge at Coalbrookdale, and every surviving Victorian cast iron arch still carrying traffic today, asks of the engineers who work around them is not whether they should be replaced. The question is whether we still know how to build something that the engineers of 2025 will be working around. The honest answer, at present, is that we are still deciding whether we consider that a worthwhile ambition. The cast iron arch has already decided. It decided in 1830. The answer was yes, and the physics has been agreeing ever since. If this subject interests you, and we suspect it does since you are still here, subscribe to the channel. There are more machines, more systems, more decisions made by engineers decades ago that are still paying off today, largely unnoticed by everyone except the people keeping them running. And if you have a connection to what we have just described, a family member who worked on something like this, a machine you have personally maintained beyond all reasonable expectation, a repair that should not have worked but did, tell us in the comments. The engineering knowledge that kept these machines alive was never written down in a form anyone thought to preserve. It lives in the people who learned it from the people who built it. We would like to hear from them before they stop answering questions.